Let's do that. So welcome everybody for the session dedicated to the most influential paper from 10 years ago, presented at ICSM. 10 years, my name is Andy Marcus. I had the pleasure and privilege to serve as program co-chair 10 years ago. If you look down in the right-hand side corner, you'll see me and then Radu Marinescu in the middle, who was the general chair of ICSME 2010. And to the right, Michele Lanza, the program co-chair. Michele is in Europe. It's, I guess, 2 a.m. for him, sleeping well. So I have the privilege to present this. On the left picture, for those of you who have seen Ahmed's keynote, he presented more picture with the soccer game. I couldn't help myself to put it there too. I'm one of those three. Michele is the one in green, I'm the one in orange, and Ahmed is the one in black. It was fun, not so much fun now virtually, but here we are. It's good. It's good to think about the past a little bit. So there's the path of ICSM that took in the last 10 years. So we've been all over the world. Unfortunately, we're not in Australia now. I was looking forward for it, but maybe next time. Let me tell you a few minutes, in a couple of minutes, about the process we followed for selecting the most influential paper. So first, approximately in March, I believe, I don't remember, something like that, Christoph and Hongyu reached out to us, being Michele Lanza and I, and asked us as program chairs of the edition from 10 years ago to come up with a process of selecting a paper, which we graciously agreed to. Well, ICSM 10 years ago had actually 84 papers in the program, combined long and short papers. We looked at all of them, not trying to be biased towards long or short. Sometimes short papers are worthy of you know, awards, and they do have influence. So in first phase, we selected 13 papers out of this, primarily, but not necessarily on citations. 4 of these papers also had journal extensions that we looked at. Michele and I then read these papers, discussed, it took a while, and finally we selected 3 of them that we felt qualified as final candidates for the most influential paper. Meanwhile, we formed an ad hoc committee. We invited 7 researchers from the field, people who have attended or attending even now ICSME. We covered a diverse range of young people, senior people, women and men, and people from most continents as much as possible. And we asked the 7 people to rank these 3 papers in order of their preference. So they ranked the 3 papers, and they give us back a list of 1, 2, 3 and short justification for that. Well, in the end, out of the 3 papers, the one that surfaced on top, the most influential paper, had 4 votes, 4 ranks 1, 2 ranks 2, and 1 rank 3. Whereas the other papers had somewhat lower ranking. Now, interesting note, actually the most influential paper doesn't have the most citations from ICSM from 10 years ago, and neither it is a paper that won a Best Paper Award back then. Proof that, not only the Best Paper awards or highest citation end up being considered most influential paper. So the 2 finalist papers that I mentioned out of the 3 are, one of them is Deriving Metric Threshold from Benchmark Data by Tiago Alves, Christian Ipman, Joost Visser. And the second paper is All Code Smells Harmful, a study of God classes and brain classes in the evolution of 3 open source systems by Stefan Ulbrich, Daniela Cruzes, Dag Sjoberg. I apologize if I butchered any name here. Well, these were the finalists, and the winner, it's not a secret because it's in the program, went to the paper on template-based reconstruction of complex refactorings by Kyle Pratt, Napol Rakadasumrit, Nikita Sudan, and Miryung Ki. Well, Miryung is here to present a retrospective of the paper. I think, if I recall correctly, Miryung, you were there in 2010 and presented the paper as well. I looked through the pictures of from 10 years ago, trying to find one of you, and I actually found one. There you are, in the audience. It's the only one I found with you. Back then you were in the audience. Now I am inviting you to take center stage, virtually speaking, and start your presentation. Thank you.
Thank you, Andy. Let me share my screen.
Oh, meanwhile, Miryung said that people are welcome to interrupt with questions. Please raise your hand, type in Slack, type in the chat, and we will direct your questions accordingly. If you want to ask during the talk. According to the plan, there should be at least 10 minutes, 15 minutes maybe at the end for additional questions.
All right. So thank you, Andy, for introduction, and thank you for the ICSME 2020 organizers for having me in this session. So my name is Miryung Kim. I'm a professor at UCLA. Today, it's really my honor to receive this most influential paper award and present our work on refactoring reconstruction. I'm representing our team, like Kyle, Nepal, and Nikita, who are graduate students and undergraduate students at UT Austin at the time. Kyle is now a senior engineer at Indeed.com and father of 2. Nepal is a PhD student at Carnegie Mellon University after spending 8 years at Microsoft as an engineer. Nikita is a senior manager at Walmart and also mother of 2. This RefFinder paper is really special to me because it is the first paper that I wrote as a faculty with my own student. All right, what was it 2010 like? I remember a devastating earthquake in Haiti, the excitement of visiting South Africa for the first time for ICSME 2010. I also recall some anxieties regarding air travel due to volcanic eruption in Iceland. But I remember it all worked out. ICSME 2010 was a wonderful experience for many of us who were there. Currently, we are in the midst of a global pandemic and we are facing uncertainties about our future. 10 years ago, I was a second-year assistant professor at UT Austin. I was also dealing with the uncertainty at the time. You know, I was excited about the opportunity to lead my own research group, but at the same time, there was some uncertainty about whether I could successfully push my own research agenda and also lead my group. Because until then, I had not written any papers with my student, you know, without actually my advisor or other collaborator. So as I was preparing this talk, I dig through some of my pictures from my old office at UT Austin. As you can see, I had some deadlines sketched on the whiteboard. I had some boxes of papers on my bookshelf. because I had two large bookshelves, but I didn't really have many books to fill. So I remember categorizing and labeling my paper boxes and keeping in my bookshelf. Kyle was a fresh graduate from, just graduated from Vanderbilt University. He was a first-year graduate student who just joined my group. Nepal was a second-year sophomore with a double major in math and electrical engineering. When he contacted me, I recall actually asking him, like, do you know how to program? Do you know Java? And if I remember correctly, I think the first answer was like soda. And the second answer is no, but I can learn. So I gave this in Nepal a Martin Fowler's Refactoring book to read. And, you know, I was actually really surprised that after like 2 or 3 weeks later, he came back and he said, I read the entire book. So that's how this like undergraduate research involving Nepal started. Nikita was also like fresh graduate from University of Maryland College Park, who did undergrad research with Viva Sazavo, who was my lab mate at the University of Washington, and at the time, assistant professor at University of Maryland College Park. Andy just showed some pictures of Timisoara and ICSME 2010. I dig through some of my old photos and then I found some of these pictures. I remember like the beautiful plaza in the town center in Timisoara. Radu was the general chair, and then Andy and Michaela was co-program chair. One of the things that I really remember about ICSM is that one of the keynote, the third keynote, was rather untraditional. They invited like 3 very young and successful researchers like Tudor Gerber, Ahmed Hassan, and Tom Zimmerman, who are very young, like compared to many of the keynote speakers. So I was really excited about the energy of the conference at the time. So no idea is born from vacuum. So maybe let me share some background and some ideas that have motivated and inspired this work on RefFinder. So it goes back to like early 2000 and mid 2000. In early 2000, with the rise of open source projects and also increasing availability of software repository data on the internet, there was an increasing interest in mining software repository research. In fact, the Mining Software Repository Conference, MSR Conference, which is a conference now, started as a workshop around that time. In 2005, as a PhD student at the University of Washington, I attended one of the earliest docs tool on this topic of a mining software repository. I met many research cohorts in this docs tool for the first time, such as Tom Zimmerman, Ahmed Hassan, Martin Pingzer, Sung-Hoon Kim, Misha Lungu, and Tudor Gerber. So after the stocks tool, I came back and my advisor and I were excited about this new area of extending a single version program analysis to multi-version program analysis. Then we decided to investigate this problem of automatically identifying corresponding code elements between program versions, multiple program versions, which is a code matching problem, but also program differencing problem. So the underlying hypothesis behind my PhD dissertation work was that even though the code edits are often represented as a line level differences per file, there is an underlying latent structure in these code edits, and we can infer these structures automatically using AI algorithms and then represent them concisely as a logic rule. So So for example, like if you look at this diff patch that may cut across like 9 different files and 723 lines of edit or deleted lines of code, it may look like sort of just a line level edit, but there may be like some underlying structure that could be set systematic and represented concisely as a rule. So for example, all methods that has a name set host, which is placed in the subtype of a service class, could have deleted API calls to SQL exec, and there could be also exceptions to the rule. They may represent missing edits or some incomplete changes that should be flagged upon. So my work was actually using some classical AI algorithms like inductive logic programming to find these rules automatically. So let me now talk about this inspiration for RefFinder. Like 3 specific inspirations that actually motivated this RefFinder work. So the first inspiration actually comes from very large body of literature on logic metaprogramming that flourished in like late 90s and early 2000s, especially when aspect-oriented programming was very hot topic. There are many who have used like logical representation of a program as a kind of knowledge base and use either data log or prolog queries to investigate program structure and search code. Second inspiration actually comes from the body of a literature that investigates like program differences and also compares the 2 program versions to detect these like high-level changes such as a rename and move refactoring. Also, there are like many others, I see Jen Chan's face over here, who share sort of the same vision that program differencing could be improved by adding more semantic layers of abstraction using like change types. So, you know, there have been like some of the early work on these refactoring reconstruction that try to extract refactoring, like API level refactoring from program version. And also, some of the people tried to make these change types explicit, which could be added layer on top of syntactic differences coming from abstract syntax AST differencing. And also, some of the people were trying to capture change in intent explicitly by recording some of the edit histories from IDE. And many of these work was actually on the level of a sort of API method level headers. And there was a like kind of growing interest among a group of researchers in this area that we were thinking now is a time that we actually need to look deeper into the changes within method bodies, analyze the control flow and data flow within method bodies to really better understand what kinds of edits are happening. Another motivation for RefFinder is actually set of unpublished negative results that I had. So during and after my dissertation work, we were trying to infer these underlying latent structures in program edits as logic rules. Initially, we were like wondering whether we can discover any rules. Once we start actually adapting and plugging in these AI algorithms, we were actually discovering too many change patterns, where many of them were actually uninteresting rules that look like a known fact about some compiler transformation. So we try many different like learning algorithms beyond like inductive logic programming, like such as statistical relational like structure learning coming from statistical machine learning, genetic programming, like heuristic search. And none of them were quite able to solve this problem of like automatically suppressing uninteresting rule as well as like, you know, prioritizing interesting rules. So in other words, like we were kind of came to the point where it's important to explicitly encode these domain-specific knowledges as a template rules, and these inductive bias needs to be specified explicitly. So this is why the title of the paper is a template-based reconstruction of a complex refactoring. It's a template-based because we wanted to encode these domain-specific knowledge of our interesting refactoring patterns as a template rule. We were targeting to infer complex refactoring, which requires analyzing fine-grained changes below the level of API method headers and look into edits within method bodies. One of the sort of the strengths or appealing factor about this work is that the work is very extensible. So people can easily add and define new refactoring rules as a logical constraints, and then these new type of refactoring could be discovered from program versions. So now in those next several slides, you're going to see the original ICSM talk in the original keynote style. So I condensed it, so it's not going to be full talk, but let me give you some high-level ideas about this work. So the motivation for RefFinder project is refactoring aware code reviews. There are times where developers see the patches and it's not few lines of a code changes, but it could be like hundreds of lines of a code changes scattered across multiple files. And you see many file level addition and deletions. These complex and non-local edits are hard to review during the code changes. So the problem we were trying to address is how can we automatically identify the location and types of a refactoring by comparing two versions of a program and making it easier to understand these code changes. So there are several challenges related to finding complex refactorings using some of the existing techniques, or like including some of the techniques that I had earlier. Complex refactorings are often composite refactoring that require identifying some prerequisite atomic refactoring. So for example, if you want to extract superclass refactoring, you need to find atomic refactoring facts such as move field refactoring or move method refactoring. So the inference algorithm must find these prerequisite refactoring first and then weave them together with other change facts using these logical constraints to find composite refactoring. Also, these complex refactoring are sometimes very fine-grained, so you need to look at information about changes within method bodies. In particular, like some of the changes to the control structure or dynamic dispatching changes happen between two versions. So our RefFinder approach is a logic query-based refactoring inference approach. It consists of 3 steps. We first encode each refactoring type from multi-filers refactoring book as a template logic rule. Then our fact extraction, the module will use abstract syntax tree analysis to extract structure change facts between two program versions, which is sort of what could be done by abstract syntax tree differencing, but these are added as a logic fact. Then lastly, using logic programming engine, like a Prolog or a data log like engine, RefFinder invokes these like logic queries, like a template queries, and find these like change facts that represent like both like atomic and composite refactoring. What's important is that we kind of order these inferences so that the prerequisite refactorings are found before you could find composite refactoring, which I'm going to explain a little bit more in detail. So RefFinder is actually built on top of like my dissertation work on LSDiff, like logical structure diff. So at the time of LSDiff work, we actually represented change facts at the level of API method level headers and like accesses and call like these type of coarse-grained dependencies. But to enable inference of a complex refactoring, we added like 14 additional predicates. Many of those are able to capture some of the changes in control flow structure of the program. But we also added like similar body predicate, which was needed to define or track movement of a code blocks between methods. So this similar body predicate is built upon some rudimentary clone detection technique based on longest common subsequence algorithm and like normalized like similarity measure, like a code similarity measure. So once we compute these facts like from each program version and represent into logical fact bases, by doing the separate differencing, we identify like change fact, like logical fact level differences between two program versions. So for example, we can see what are the edit methods, like what kinds of conditionals or call accesses were deleted. Now, let me talk about how this Refinder approach works. Like, I'm going to first describe like how you could represent like a collapse hierarchy refactoring as an example in terms of logic rule, and then how these logic rules are used to identify these composite refactoring facts. So consider this a collapse hierarchy refactoring. This refactoring is about like merging superclass and subclass together because they're not very much different. So it's about actually moving methods and fields across the class hierarchy, which is also called as a pull-up method or push-down method. So if it is moved from supertype to subtype, it's called push-down. If it is moved up from the subtype to supertype, then it's called a push-up. So each like template rule represents like inference of refactoring. So for example, if you want to find collapse hierarchy refactoring, these rules are consequent. The right-hand side refers to target refactoring to be inferred. The rules, the left-hand side, like rules antecedent, refers to structural constraints of our program before and after the target refactoring. So as you can see, these rules antecedent could consist of like prerequisite refactoring types in addition to atomic change effect. So for example, finding collapse hierarchy refactoring requires knowing presence of either pull-up field or method refactoring or push-down method or field refactoring. This was actually really painstaking work. What we done, that Kyle and Nikita and Nepal did together is that we took this book of Martin Fowler's refactoring book, and then we painstakingly actually manually converted them to logical constraints. I do remember some of the students were asking, do we really need to try like all? But one of the things that we were trying to argue was the comprehensibility and extensibility. With the energy and enthusiasm, we kind of pushed it through. So we ended up encoding like 63 refactoring types in terms of logical constraint. Some of them we actually had to exclude because they were either too ambiguous, it required actually aliasing analysis, or clone detection at an arbitrary granularity, which was kind of hard to encode as a logical fact. So like, for example, to infer collapse hierarchy, as I said, we need to go from inferring move method or field refactoring and go up, either referring push down or pull up field and method refactoring. So here's how it works. The RefFinder will start finding these atomic refactoring. So to find move refactoring, you need to look up these move refactoring rule. And if the antecedents are like satisfiable within the logic fact base, we will match that and then add a new field, new logic facts or change facts on the fly. And then this will enable us to look at next refactoring, pull-up field refactoring using move field and before subtype facts together. Then if this is satisfied and new also like pull-up field facts are added to the logic database on the fly, this will allow us then to infer collapse hierarchy refactoring facts. And this will then like later added to this. So in terms of evaluation, we actually use two different methods. One is actually doing some sanity check with respect to code examples from Fowler's textbook. So Kyle and Nepal, especially Nepal, did a lot of work in creating these examples from Fowler's textbook, collecting them, and then we created this ground truth data set of what are the refactorings that we want to find and what each type represent. So we evaluated precision and recall using Fowler's examples. We also applied to open source project. I think we were targeting 3 different projects at the time. And what we have done is that we actually use a very low threshold, the similarity threshold, to find larger number of refactoring. Then we manually inspected them and identify what are the actually true refactoring that we can validate. Then we use a sort of default threshold and try to see whether we can find these refactoring facts. So we were, finding these refactorings with about 74% precision and 96% recall. So low precision came from 2 reasons. One was our sort of method name comparison was rudimentary, sometimes ignoring the input signature of a method, and also our the code body block movement tracking methods based on rudimentary clone detection technique. Sometimes it created first positive matches or first negative matches, which led to sort of the low precision or not so great precision. All right. So now, I wanted to share some of the reflections on the RefFinder paper and how this paper has impacted me and my research group, as well as, how it might have affected other people's work in our community of software maintenance and evolution, and broadly software engineering. So software engineering community, really took this work on refactoring reconstruction, not just my own work, but a lot of other people's work on refactoring reconstruction to several directions. I knew some of these work, many of these work actually by reading papers, but this time I was actually going through some of the reverse citations to RefFinder work. And I saw this work on inferring refactoring edits between 2 program versions has been used for many different purposes. Some of them used to build IDE and tool support to support these real-world refactoring that may not be semantic preserving transformations only. Some of them actually use these capability to find refactoring, to investigate the role of a technical debt and code smells and how refactoring may be able to cope with this or address this problem of a technical debt and code smell. Some of the people took this work towards the direction of automated clone removal and code extraction. So, there has been some work that's automating some of the needed refactoring based on initial evidence of found refactoring edits. Some were also using this to recommend additional related refactorings that people could do. Some actually took this work towards the direction of testing and dynamic analysis that are refactoring aware, that could prioritize regression test strategy based on refactoring edits. Or some took it to the direction of finding errors within the refactoring, because refactoring may not be strictly semantic preserving transformation, and finding this initial evidence of a refactoring and comparing against pure refactoring may give us real errors that could change the code semantics. Some took it to the direction of a multi-objective, search-based refactoring. Some used it for improving code review practices or better detect merge conflict. Some use it for automated change or release note documentation or summary description, automated summary for change. Some also took it to the direction of improving the refactoring reconstruction technique itself. improving its accuracy, efficiency, or some of them are targeting these diff or delta as opposed to looking at the whole program versions before and after. There were many lines of work that really came out of it, so I probably don't have a time to go into like details of an individual line of work, but maybe let me share one line of work on developing IDE and tool support for like real-world refactoring that I'm very familiar with. So refactoring is a field that goes back to early 90s, and by 2000, refactoring menu became a standard part of a feature in many different mainstream like IDEs, such as Visual Studio, Eclipse, or IntelliJ. So if you go to your favorite IDE, you can see a refactoring menu, and if you click, the drop-down menu will show like maybe 10 different refactoring types that is completely automated in the IDE sense. But around like late 2000, like 2009, with Emerson Murphy-Hill and many others, there has been some growing skepticism about, despite this like advance of moving software engineering research and automated transformation to IDE, people are not really using refactoring features, and this is not how they actually do refactoring to cope with the technical debt in the system. We were investigating like how people actually do refactoring and why these automated features are not underused or misused. There was actually friendly competition between my group at UT Austin, Ralph Johnson, Danny Dick, and University of Illinois Urbana-Champaign, and also Emerson Murphy-Hill's group at like NCSU. We were all trying to understand what real-world refactoring really mean, like how it made these manual refactoring may differ from automated refactoring, how we can better support the practices in the real world. So this insight that embraces that how real-world refactoring may go beyond these rudimentary semantic preserving transformations, such as a rename method refactoring or rename variable refactoring that you see and often use in IDE, created this body of work and tool support try to support both the semantic preserving refactoring and semantic modifying transformation, and how to also better support this combination or interleaved like manual and automated refactoring together. So many of these lines of work actually use like RefFinder's capability to discover refactoring from program edit. So once you see the evidence of some refactoring, use automated refactoring to automatically complete the rest of the refactoring. Some took it to the direction of a refactoring aware code review, where we not only automate the transformation, but trying to difference against the manual edit to find potential errors in refactoring edit, or at least surface that information about how semantic modifying change may be different from pure refactoring. And some of them were like, trying to use this information again to help with a kind of refactoring validation. So as I reflect on this larger body of work, builds on refactoring, reconstruction, and some of the work on RefFinder, I really observed that software engineering community took this work to multiple directions. I cannot mention all names and faces here. I apologize in advance, but many of this great work is actually done by young researchers who brought their own color and taste and creativity to expand this field of refactoring research beyond automated transformation. Refactoring is no longer about automated program transformation feature in IDE. Now this area of research became about testing, recommendation system, automated documentation. I'm really proud and also thankful to many who are have done research in this area, as they are now tenured and tenure track professors who are also leading their own research program. Some of them are continuing research and expanding this research field. What probably enabled others to build upon this refactoring, reconstruction, and Reffinder work is that we released the tool to public, both as an IDE plugin, but also as a standalone tool that others could use. So we actually demoed this Reffinder at FSC same year. As you can see, this is like the Eclipse plugin. You can see the side-by-side differences. Program differences side-by-side view, and we will present a list of refactorings that are found. If you click on individual refactoring, you can see logical change facts that supports this inference. If you click on any of these change fact, it will automatically navigate to the particular location. So it could kind of support program comprehension as well as a code review process. Personally speaking, this Reffinder work also enabled me to receive a Microsoft SIFA award, like Software Engineering Innovation Foundation award. But for me, it was not just an award or industry funding, but really a collaboration opportunity that led to subsequent visits to Microsoft research and work on something much bigger and exciting, such as studying refactoring practices in the wild with the real world professional developers, and quantifying the impact of a multi-year Windows re-architecting, which is probably the largest scale refactoring to date. I'm also proud that Nepal continued the research on RefFinder and made it as an independent topic and his honors thesis. He designed this new dynamic change impact analysis that combines the change impact analysis with the refactoring reconstruction. When I first met Nepal, he did not know objective-oriented programming and Java. And his independent research for 3 years eventually led to solid research paper and a first author paper at ICSME in 2012. So, and Nepal, who went on to Microsoft to be an engineer and practitioner for 8 years, actually recently decided to go back to Carnegie Mellon University to pursue PhD. So I sometimes wonder whether any research experience might have helped him to make that decision. So, yeah. As I was preparing this slides, it gave me an opportunity to really reflect. I'm very thankful to my former and current student. So when I started my faculty job 12 years ago, I had this vague hypothesis that among the line level diffs and differences that we see in GitHub pull requests or version control system commit, there is an underlying latent structure. And by making this structure explicit, we can enhance code review, automated program transformation, and bug detection. I'm thankful to my students who trusted me and gave me the opportunity to mature these ideas to something concrete and substantial and creative together, because it's really my students who put their efforts and perseverance to really carry on these vague hypotheses into something more mature and concrete. There is always a first time for everyone. You are invited and entrusted with the opportunity to carry out something that you've never done before. And ICSME, ICSME community in many ways provided me that first opportunity many times. I am very thankful to ICSME community for really giving me that opportunity. 2009, it was my first PC invitation. 2011, Andy invited me to be an ERA track co-chair with Max DePenta. And that was my first co-chair experience, as well as first organizing committee experience. It was also my first PC co-chair experience in 2019, working with the ARPA Bassett. And I'm thankful to Jonathan Malektig and steering committee for trusting me with such responsibility. So I want to conclude this talk. I want to thank my advisor, David Knockin, who passed away in 2013. David's warmth, genuine interest in listening to and understanding individuals, rather than just solving technical problem and technical research problem or producing research paper, made me to choose software engineering as a field and community that I wanted to be part of. Thank you.
I guess we do virtual applause. Thank you very much, Miryung. Well, we do as planned. We have approximately 12 minutes for questions, 10, 12 minutes. Please don't be shy. Raise your hand or type question. Okay, we have a comment from Tushar Sharma. Let me read it out loud because Miryung doesn't see it on the screen. Thanks for the nice talk. I echo that. Though you have covered various refactoring aspects and contributions from various groups, how do you see from a bird's eye perspective the landscape of the research field changing in the past 5 to 10 years? That's question number one. Question number two, also, what kind of challenges do you think are prominent that the community may consider looking into?
That's a really tough question. I think if I look at the bird's eye view, I saw probably the landscape of a research field on refactoring getting more closely tied to empirical studies, mining software repository, as well as a software quality research. So I think this notion that refactoring could help cope with the technical debt or remove software quality problem. I think there has been really increasing effort to see actual evidence that whether refactoring is done to correct these issues, what are the costs of a refactoring and what are the benefits of a refactoring, and quantifying that. I see a lot of research really flourishing in that direction. Another direction that I saw is accepting or broadening notion of a refactoring. Refactoring may not be semantic preserving transformation only, but a broad set of quality enhancement effort. So I think both tool support, testing, and I think a lot of these work sort of stay away from these neat program transformation, such as a rename variable refactoring or rename method refactoring, but moving towards more broader effort of trying to find cope with these cost smells or quality issues. So that's my answer. The second question is, where is challenges that we need to look into in the future moving forward? I think one of the always challenges that we had as a field is access to professional developers and understanding how they actually use refactoring and really examining the benefit. So, this availability of an internet scale corpora that we see in open source is both kind of double whammy. It's a two-sided coin. One, because of the availability of data, it's very exciting and in some sense tempting to do research because of the data, but also it makes sometimes the research to be a little bit shallow because you may not really fully understand why people are doing it or how they did it, but because of availability of data, you start crunching numbers. So I think that, I'm hoping that there is a more in-depth involvement of a professional developer in the loop in this line of work. And I think the challenge is kind of can we work together with this developer or more industry population. So.
All right, here's another question from Zhenchang. I see you're now helping data scientists write software. do you see they also have need for refactoring, and how their needs differ from normal developers? I guess they're not abnormal, right?
No. All right. So actually, around like 2014 or 2015, I had a little bit of a change of heart, and I moved on to this field of understanding data scientists, data science practices, and like big data analytics support. I think it was more of a like just interest. And initially, I actually wanted to see whether there was a lot of refactoring opportunities. So for example, like RStudio or Jupyter Notebook, compared to like IDE support, I think a tool support for this domain of a data scientist or is still lacking. So I see a lot of opportunity. I think there is a need too, like, you know, because like Jupyter Notebook, for example, environment is much different from IDE. So I think there are needs. I think this is a kind of exciting area. Yeah.
Okay, any more questions? Don't be shy. Some live question rather than typed questions, anybody? Okay, while you're thinking about that, I have a question, Miryung. So, especially that I was flipping the pages on Zoom and seeing quite a few young faces makes me feel old, although I'm not that old, right? Anyway, I know that when I was a grad student or a fresh graduate, I did not envision that 10 years later I'll be still working on the same topic than I did at the time, right? I thought I'm gonna get either A, tired, B, finished with it, or you know, generally speaking, moving on. Well, I was looking at your DBLP page, and I noticed that even now in 2020, you still have composite refactoring papers, right? So there you go. You spent 10 years, more than 10 years, right, on studying changes in software and specifically focusing on refactoring on top of the newer topic you're doing, right, or rather before. My question is, you mentioned at some point you had a hypothesis back then that there is some structure there available in the repository that we can leverage. Still, going back to 10 years ago or more, what are your thoughts in terms of, I don't know, what things from back then turned out to be the way you envisioned and what turned out to be the opposite?
Okay. Actually, great question. So, you know, Andy, actually, I think sometimes I kind of pulled into what I was doing or the same ideas that come back in a different way. Sometimes I actively try to move away and then like, you know, I think you have a similar experience. So sometimes when we are doing reviewing, sometimes like the editor knows you or like, the chief editor knows you, so you get the same assignment all the time. For me, for example, it's like refactoring clone detection, you know, so I'm pretty sure for you, it's like information retrieval always coming back to you, right? So, but I think maybe my, you know, the scope actually has changed or perspective has changed. I think when I graduated from PhD, I was looking for evidence of a systematic structure, but it was very much inspired by redundancies in code or redundancies in change. I think it's partially because I have done some work on code clones, and then that was sort of forming my direction. Later on, like I guess I started looking a little bit more onto like different types of dependencies that are underlying in the structure. So I think it was like broadening a little bit, but sometimes these forces pull you back too. So one of my recent graduates, like Tianyi Zhang and I did work like at the kind of mining software repository, API usage mining. We're looking at redundancies at a much bigger scale, but I think some of these redundancies were coming back to us. So.
Thank you. Any other questions? Oh, there you go. We have a question. Let me read it. Data scientists often work with well-formed tools and infrastructures. Do they need to consider the quote-unquote design of their data analysis applications? And it follows up, refactoring is highly related to design. So I guess the refactoring needs of data scientists may be different from those of normal developers. I guess that is both in response to your response to Zhenchang's question.
Yeah, I mean, so in that sense, I resonate with this question. So when you look at the history of, refactoring research, actually design patterns precedes research on refactoring. I think once the people start understanding what are the kind of common ways to design or redesign the system in object-oriented programming domain, like people start figuring out how to then automate it, right? Do we have an understanding and depth of understanding of what are the effective design in building data analytics software? I think, to me, that's unknown right now, right? Actually, sometimes some of my machine learning colleagues come back and ask, like, do you know design patterns for machine learning system, right? I don't know. I think that's an exciting field, right? How do we engineer what are the design patterns? I mean, in many ways, this is unrelated to my talk, but I think Andy or some of the more senior researchers will remember. I think in 90s, like there were more papers on design and architecture, right? Without like significant like number crunching, you were able to write papers with the insights and ideas, right? But I think now our field became very numeric and quantitative. And it's very hard to write design papers, right? So, yeah.
Sorry, any other questions? Well, we're just about on time and 1 minute. So tell us in 30 seconds, are you still gonna work on refactoring a mining software repository 10 years from now?
We are facing uncertainties in this global pandemic, so I think it's very hard to predict what will be 10 years. I think maybe we'll be able to have a retrospective conversation. But what I'm really hoping is that all of us could see each other safely face to face, right? So, and some of us will do refactoring research too.
So the answer is yes.
Yes.
Okay. Thank you. Thank you very much, Miryung, again. Congratulations for the award. A very good presentation. Thank you for all the questions. And I guess our time is up. I don't know what the next session is, but we have Hongyu here and Christoph and Zhenchang and Kelly to tell us. I'm signing off. Thank you. Bye-bye.
Thank you.
Thanks, Miryung. Thanks, Hongyu. Thanks, Andy.
Thank you, Andy.